Alright, so let's take a look at example 1. So example 1 asks us to find the partial derivative of f with respect to x and with respect to y of this function here. Now because we have to find the partial derivative with respect to x and with respect to y, and we're finding a second order partial derivative, if we can apply Clairaut's theorem, that means we could do it in either order, with respect to x first or with respect to y first. So we should take a look to see if one of those ways is going to make more sense than the other, and also, well, we need our function to be continuous for that to happen. So the first part, 3x to the 5th plus 7y squared, the entire quantity to the 8th, well, that's all polynomial, so that's definitely continuous. I can apply Clairaut's theorem, at least to that part. But I have x's and y's together, so it doesn't seem like there's a better choice for that part. Second part, the inverse tangent of x squared plus 2x plus 1. Well, that's another continuous function that exists from negative infinity to positive infinity. Except this one has, well, only x's in it. Which means if I take the derivative with respect to y first, well, that's all a constant, which means the derivative of a constant is 0. And I'm going to be able to just get rid of that entire thing. If I did it with respect to x first, well, I would have to actually go through and find the derivative of the inverse tangent and, well, apply chain rule to that function on the inside. So we're definitely going to do this with respect to y first. So my notation, that partial notation, it's called a del, but we're just going to call it partial. So partial y of 3x to the 5th plus 7y squared all to the 8th. And again, we're going to split this up. Plus the partial y of the tangent inverse of x squared plus 2x plus 1. And again, the nice part is, I know that since this is a y, it's with respect to y, but the only variables are x's, means it's a constant, and this entire thing is just going to 0. Which means I really only have to evaluate this part. So the partial with respect to y of this entire thing, except, well, I definitely see exponents inside of exponents. So we're going to have to use the chain rule. So let's get our scrap paper out and do the chain rule. Alright, time for our scrap work on the chain rule. So we're taking the partial with respect to y of, again, this entire quantity to the 8th power. Obviously we're using chain rule because we have a composite function here. And when we do the chain rule with composite functions, we pick our u to be the inside function. And clearly the inside function is going to be the entire expression 3x to the 5th plus 7y squared. And again, the whole point of doing the chain rule is that we can take this whole expression and instead do it as the partial with respect to y of u to the 8th. Right? Because this is a very nice, neat, easy expression for us to take the derivative of. Except, well, wait a second. Our variables don't match. I have a u and a y. Well, to make them match, I'm going to need, well, a u. So I need basically a bunch of u's here. But what we're really going to do is kind of swap it around a little bit. And if I want to take this partial u, I'm going to need a du dy to make sure that, again, all my variables match. So now I'll be able to take this derivative, but I have to introduce this term to make sure it all stays equal. And so that means up here with my u, I'm going to need to take du dy. I'm going to need to take it with respect to y. Now, we do the derivative one step at a time. The derivative of 3x to the 5th with respect to y, that's a constant. It goes away, that's 0. And the derivative of 7y squared with respect to y is 14y. Now, we can go through and take a look at this problem and see that I have my du dy in the front. And then this part, the derivative of u to the 8th with respect to u is 8u to the 7th. And then all we have to do is just plug in our original u, plug in our du that we found, And we're done with this part of the problem. So it looks like that partial with respect to y is going to be 14y times 8, the quantity 3x to the 5th, plus 7y squared, all to the 7th power. And, well, when we bring it back to our actual problem, let's actually combine the 14 and the 8 together to make it a little bit neater, so it'll be 112 as my coefficient. So we bring our answer from our scrap work back. Here's our partial with respect to y. So now the next step is to take this partial with respect to y and take it with respect to x, which means partial x of this entire thing, 112y, 3x to the 5th, plus 7y squared. Now that entire quantity is to the 7th power. But again, it's respect to x, which means anything that just has a y is a constant, which means, oh, this is a constant. So I'm going to be able to factor this out. And then I'll just have to work on taking the derivative with respect to x of this part, which, oh, is going to require another application of our chain rule. Back to the scrap paper. All right, time for the chain rule once again. This time, we're doing it with respect to x. Our expression is to the 7th power, but again, it's a composite function. My inside function, u, is actually going to be the same one as it was last time. Now, the idea, of course, is that I want to bring this all the way down here. So if I am the partial with respect to x of a much simpler expression, in this case, u to the 7, because I know how to take that derivative if it's with respect to, well, u. Which means I need to introduce u's. So du and du. And then essentially what we're going to be doing is swapping denominators, because we treat them like fractions, right? I can multiply fractions in any order to make this into du dx and then partial du. Now, again, technically they're not fractions, and you really can't do that technically, but you can because it actually works. And if you're an engineer, that's fine. You'll pretty much always be able to do this. If you're a mathematician, it's a little bit more complicated. We can definitely do this, but it's not necessarily the exact rules of fractions from before. But we should be okay. Either way, when we come back to the problem, well, I need a du dx this time. Well, here's my u. I need to find my du dx. So now I'm finding the derivative of u with, well, respect to x. So the derivative of 3x to the 5th, 15x to the 4th, and then my 7y squared, well, that's a constant. That completely goes away. So, when I take my derivative, I have my du dx. The derivative of u to the 7th with respect to u is 7u to the 6th. And so, when I just bring it all back together, I'm going to get 15x to the 4th times 7 times the quantity 3x to the 5th plus 7y squared, all to the 6th power. And again, when we bring this back to the rest of the problem, we should probably combine the 15 and the 7 together to make it a little bit neater. But let's bring it back right now and finish this problem up. So, we bring back our result from our chain rule work. We factored out the 112y, and we're, well, pretty much done. We have the partial with respect to y and x. Now, Clairaut's theorem says we could write it either way, and I guess technically the problem is written partial xy, so we could definitely do that if we want. When we combine our coefficients, 112 times 15, 11,760, x to the 4th, y, and then my entire quantity, 3x to the 5th plus 7y squared, all to the 6th. And there is the solution to this problem.